Good morning and welcome to this paper presentation on Fairea, a model behavior mutation approach to benchmarking bias mitigation methods. I'm Max Hall, and I'm happy to present you this joint work with Jia Zhang, Federica Sauro, and Mark Harman, all who are from University College London and the Solar Research Group. Today we will continue by looking into some background on fairness and software fairness, and then move on to the contents of this paper.
Let's have a look at what we define as fairness and what fair treatment of individuals is. In particular, we follow the idea that fairness is achieved once individuals are treated based on merit and not sensitive attributes. Examples for such attributes are gender or race, which you don't want to use to treat people differently. Because something that can happen if you don't take this into consideration is that you divide the population into two groups. The first one being the privileged group and an unprivileged group. Whereas the privileged group receives a systematic favorable treatment as opposed to the unprivileged group. We can see this in an example on how to determine and measure fairness or the degree of bias in a classification model. You can see the two groups, whereas the privileged group has 8 individuals and 6 of which receive a favorable treatment, which is represented by the smiling faces. That ends up in a total of 75% of the privileged group. The unprivileged group, however, has 6 individuals, 3 of which receive a favorable treatment, therefore being a total of 50%. If we compare those two numbers, we can see that there's a disparity of 25%. Therefore, we treat the two groups not equally. And this is comparable to the statistical parity difference, the fairness metric, which we use in our experiments. So once you are able to measure the degree of bias, you can try to reduce the bias by applying bias mitigation methods. In particular, they can be applied at 3 different stages of the development process. At first, there's preprocessing, which applies changes to the training data, which follows the goal that you try to prevent the bias from reaching the models. Secondly, there's in-processing, which applies changes to the algorithms themselves. And lastly, post-processing, for which it is difficult to find a suitable icon, but what it does is you apply changes once the model has been trained successfully. One example could be the adaptation of predictions made by a classification model. These 3 methods have something in common, which is the intuition that fairness comes at a price. So in order to reduce bias, you need to sacrifice oftentimes accuracy. So you could say that accuracy and fairness are 2 conflicting goals, which is also represented by the term fairness-accuracy trade-off. So in order to achieve fairness, you need to reduce accuracy of the model. And we will look into different outcomes of applying bias mitigation methods to a classification model in the following.
We will now have a closer look at the different bias mitigation regions, and in the image on my right you can see the original model represented by a yellow square, which is a classification model without any bias mitigation methods applied to it. Therefore, the accuracy is relatively high, but it also shows a high degree of bias. If we now apply bias mitigation methods, changes can arise in 4 directions. For once, accuracy can decrease and increase, and likewise bias can increase and decrease as well. On the left-hand side of the original model, we see 2 regions which increase bias, which is the inverted trade-off region and the lose-lose region. The inverted trade-off region increases accuracy and therefore changes our notion of the fairness-accuracy trade-off by sacrificing fairness for accuracy, and the lose-lose region, which makes both goals worse. In general, we are not interested in the 2 regions, as they do not manage to reduce bias. Therefore, we move on to the right-hand side of the original model, which shows 2 regions that are able to decrease bias. On one hand side, the win-win region, which also increases accuracy. If that happens, it is great because both goals are satisfied. However, it does not happen as frequently. And our main focus will be on the trade-off region, in which accuracy is sacrificed in order to reduce bias.
So now let's have a closer look at the trade-off region. And what we want to ask ourselves is, Once you apply a bias mitigation method to the original model represented by the yellow square, the accuracy and bias changes, so it could be anywhere in this region. For simplification, we just put a few dots where the model could end up, but in the end it could be anywhere in this region. So the first question we ask ourselves is, are all those dots equal, or are there differences? In particular, all of those have in common that they sacrifice accuracy to decrease bias. But that does not necessarily mean that they are efficient. What if one of those models sacrifices too much accuracy? We want to focus on that and try to separate the area to divide it into two parts by using something what we call a baseline. So you can imagine the baseline as being a very naive approach to mitigating bias, and everything that's not able to be above the baseline, so everything below the baseline, is worse than the naive approach. Therefore, it is sacrificing too much accuracy for the degree of bias it's achieving. And everything above the baseline achieves a good trade-off, and this is the area we are most interested in, so we want to know the good trade-off. And then, so now in order to understand how we create the baseline, we want to focus on the two extremes we have. So on the top right, there's the original model with the highest accuracy and highest bias. And on the bottom left, we need to find the point with the lowest bias and also the lowest accuracy possible. And we do this by mutating the behavior of the classification model. In particular, we came to the conclusion that the best fairness or the lowest bias is achieved by, for example, always saying yes. Imagine you are at a bank and you give credits to people, and whoever comes to you, you give them a credit. You say yes all the time. Therefore, you don't have any disparity in the treatment anymore because everyone receives the same favor. And this also follows the idea of zero normalization that says once that everyone receives the same label, fairness metrics are minimized. And this helps us to create the baseline. For more details, you can check the paper to know how we create the stages in between, but this gives you an idea on how we create the two extreme points and then try to connect them with a baseline. We use this to determine how many bias mitigation methods on several data sets and fairness metrics on which region and compute the distribution. The two most interesting figures or numbers from this chart are the 34% in the good trade-off region and the 15% underneath our baseline. So we successfully are able to detect 15% of the bias mitigation methods which achieve a bad trade-off, which previously would not have been detected. This is already quite successful, and we now focus on the 34%, which are good trade-offs. Especially we are interested to represent the quality of a bias mitigation method by a single number. So instead of representing it by the accuracy and bias it achieves, we want to give them a score based on the goodness of the fairness accuracy trade-off, which then allows a more simple comparison of multiple methods. And we do this by drawing the bias mitigation method, connecting it to the baseline, and then computing the area above the baseline. The higher the area, the better the trade-off. And this can be used by practitioners to motivate the choices of which bias mitigation methods is most efficient for their use case. If you're interested in particular numbers, you can check out the second and third research question. And now, to summarize, we devised trade-off regions. We create a baseline to separate the good trade-off region from the bad trade-off region, and compute areas to determine the quality of trade-offs achieved by bias mitigation methods if they are part of the good trade-off region. You can find resources such as the camera-ready version of the paper and the replication package online by scanning the QR codes.